All right, so let's pick up where we left off last time. All right, we introduced this strong base, LDA. All right, this is a very strong and bulky base capable of deprotonating alpha carbons of ketones and aldehydes. Okay. I don't know if we looked at the structure last time, but it's a nitrogen. I don't remember exactly how many carbons, but it's got these big bulky iso. I don't remember if they're isopropyl or isobutyl groups. Doesn't really matter. But we have a nitrogen with a negative charge, very strong base, but it's got these big bulky carbons on there, these big bulky groups, right? So it'd be considered a bulky base, meaning it's not going to be a nucleophile at all. You're not going to have any substitution product, only your acid-base reaction, right? So the idea was we could take an aldehyde or ketone by treating it with LDA. We will deprotonate that alpha carbon creating one of those enolate ions. All right, and remember the big difference between using this and say sodium hydroxide is this reaction is 100% efficient favoring that product side, right? So this would be a way of creating a beaker full of enolate ion, for example. Okay. There's another one that we've seen before and we're going to reintroduce here, sodium hydride. This is also a very strong but very small base and is also capable of deprotonating alpha carbons. All right, so for example, if we took our same acetone and instead had treated it with sodium hydride, we would also create a beaker full of enolate ion. All right, so these are both two bases, two very strong bases that we can use to get rid of that alpha hydrogen. All right, so then what's the difference between these two? Well, again, one of them is a bulky base and the other one is a really tiny base. So now let's take a look at a different aldehyde or ketone. I'm going to put it in the middle here. And this time we're going to look at an asymmetric aldehyde or ketone. In this case, it's a ketone, I guess. Okay, so because that LDA is such a big, bulky base, all right, which one of these two alpha carbons do we think it's going to have an easier time deprotonating? Blue or green? Blue. So this big, bulky base, it cannot easily access carbons that are sterically hindered, And so it is going to prefer the more accessible alpha carbon. All right, and truthfully in the lab, we can make this way more dramatic by also carrying this out at low temperatures. So LDA, low temperatures. All right, that will favor our more accessible alpha carbon. Okay? If we use our teeny tiny base, sodium hydride, all right, this is going to favor the other carbon. All right, so why is that? That might be kind of hard to see when we use this form of our enolate ion. But everybody take a second and draw me that other resonance contributor of that enolate ion. Remember where the name comes from. The enol. All right, so to be clear, if I were to draw my arrows here, this pair of electrons forms that double bond, and the oxygen would then have the negative charge in my other resonance contributor. All right, and so why is the green carbon more favored? We have that more substituted enolate, right? So this one, the green one's actually the more thermodynamically stable, right? So, and again, we can kind of make this even more dramatic, preferring that thermodynamic product by carrying this reaction out at high temperatures. And we've seen this tuning before, right? That more accessible, that's our kinetic product, the one that will happen quicker because that LDA is so big and bulky and can only get to that more accessible carbon, right? But if we use sodium hydride at high temperatures, this will prefer our thermodynamic product, which is going to be the more substituted enolate ion. I'm going to move this up. Cool. All right, so basically we have these two different bases that we can use to create these different enolate ions, right? If we use the big bulky base at low temperatures, we'll get the more accessible enolate ion where that negative charge is on the more accessible carbon. If we use our teeny tiny base at high temperatures, we'll get that more stable, more substituted enolate ion, all right? And so we can take these and react it with any one of our electrophiles. So we've seen three different ones. Well, we've seen two different ones that we've used in this chapter before. Just aldehydes and ketones. Those were our aldol reactions. We talked about Claisen reactions, which is when we use an ester. All right, we can even just use a simple electrophile, our most simple that we've seen in this course, an alkyl halide. All right, so let's do our product. If we reacted either one of these enolate ions with this alkyl halide here. Everybody take a second and tell me what my product will be in this reaction. All right, looking at this reaction here, what is my nucleophile in this reaction? The alpha carbon, all that negative charge for my nucleophile. And what's the electrophile in this reaction? Going to be that carbon with that good leaving group. All right, so nucleophile, attack electrophile, and we get our substitution reaction. All right, so I'm going to be good and use my coloring here. I'm going to start by redrawing that nucleophile. All right, we have this new carbon-carbon bond. And what's on the other end of that new carbon-carbon bond? It's going to be from my alkyl halide. All right, so if you have not already, take a second, given what we just did over here, predict the product over on this side. All right, again, what's your nucleophile? What's your electrophile? What's your new bond that's going to be formed? Okay. So now, because I used that teeny base, my enolate ion didn't form on the left. It's formed on that more substituted carbon on the right. So that's going to be my nucleophile and kick off that good leaving group, that bromide. All right, so again, I'm going to start by redrawing my nucleophile. And now from that green carbon, I have my new carbon-carbon bond. On the other side has to be my electrophile. And then I'm going to be good and add on that second carbon from my electrophile. All right, so depending on what base we use, we can form our enolate ion on either the more accessible side, or by using the teeny tiny base, we can form our enolate ion on the more substituted side, and that changes which alpha carbon is playing the role of the nucleophile in our reaction. Okay? So this we practiced by using that electrophile, that alkyl halide. Let's just do two more examples for the sake of practice here. All right, I'm going to take butanone. And first, I'm going to treat this butanone with that bulky base at low temperatures. All right, and then I'm going to introduce a ketone. All right, you have an acidic workup step at the end as well. All right, and then in my next reaction scheme, I'm going to also treat this with one of those strong bases, but this time I'm going to use the teeny tiny sodium hydride at high temperatures. And instead of using a ketone, I'm going to use an ester. All right. See if you can't tell me what my products are in these two different reaction schemes. All right, so let's split this up here. I'm going to use this LDA at low temperatures, and where's my enolate ion going to form? On the blue or the green carbon? Blue, the more accessible carbon, bulky base at low temperatures. All right, so if we look here, now we're going to mix in acetone. Let me just move this thing over. our alpha carbon is our nucleophile, so what's going to be our electrophile here? That carbonyl carbon. Right, so our nucleophile is going to attack our electrophile, and whenever that carbonyl carbon gets attacked, we kick that pair of electrons up onto that oxygen. All right, so again, I'm going to start by redrawing that nucleophile. I'm going to make my new carbon-carbon bond. And what carbon has to be on the other side? That orange one. My electrophile. Cool, so now I'm going to draw those other two carbons in, as well as my oxygen, which now has accepted that extra pair of electrons, so it's got a negative charge. All right. What do we call these intermediates that we get here? These tetrahedral intermediates. Now remember, we are going to get into this habit where we see our tetrahedral intermediate, and what are we going to ask ourselves? All right, so is there a good leaving group? Because this pair of electrons would love to be able to come back down and reform that carbonyl, but it can only do so if it kicks off a leaving group. Does this molecule have any good leaving groups attached to that tetrahedral carbon? No. So the only thing it's stuck, all right? So the only thing we can do is that very last step, that acidic workup. Where we protonate that oxygen, giving us that aldol addition product. All right, so because we used this ketone as our electrophile, what we have here is an aldol addition. If instead I had had acetone and heat, we'd get that condensation product where we'd form that carbon-carbon double bond. I don't have any heat here, all right, but importantly, I used a ketone as my electrophile, so I have this aldol addition reaction, right? Where we have a carbonyl group and an alcohol group, and we said we had this kind of double check that we could use to make sure that we formed our products correctly, right? Does anybody remember that? The rule of three, right? So start counting from that carbonyl carbon, 1, 2, 3. Our new bond should be between carbons 2 and 3. All right, so this is just kind of a double check that we can use to make sure we've drawn our addition product correct. We also have that other check that we always do and is a great idea when we're forming new carbon-carbon bonds, which is to just double check by counting carbons. Right, so little checks that you can do at the end to make sure that your product makes sense, because you're going to get some big ugly products on the other side here. Right, this thing right here. There is a lot going on, so you want to be able to kind of break it up and make sure that you can see what's what. All right, so now we're going to do something very similar, but instead we're going to use our teeny tiny base and high temperatures. All right, so now where's our enolate ion going to form? Blue or green? Now we're going to get that more substituted thermodynamic product. All right, and because we have our not ketone or aldehyde, but ester electrophile here, this would fall under that Claisen condensation category. All right, what's going to play the role of the electrophile? Again, that electrophilic carbonyl carbon. All right, so my nucleophile attacks my electrophile. Again, carbonyl carbon's so good at accepting electrons because it can kick this up and never break its octet. All right, so I'm going to start by redrawing my nucleophile. When I put in my new bond, what's got to be on the other side? That orange carbon. All right, again, I got to include everything about that orange carbon. So it's got a methyl group on one side. It's got that alkoxide ion. And then it's got, because it's an ester, that methoxy group. All right, and again, we have this tetrahedral intermediate. All right, do we have a leaving group?
Would it technically be the ester?
Exactly, that oxygen, right? So now this pair of electrons can come back down and kick off that methoxy group. So remember, at the end of our Claisen reactions, we don't have a carbonyl group and an alcohol. We instead have two carbonyl groups. Right? That carbonyl reforms at that same place, that same orange carbon. All right, and again, we can use our rule of three here. 1, 2, 3. Our new bond is indeed between carbons 2 and 3. All right, we got to start counting at that carbonyl of our nucleophile. I guess we can just make a note. Since we got two carbonyl groups here, we're going to start counting at our nucleophile carbonyl. All right. Cool. So we want to have these in our notes because there are two really important things that get illustrated here. Number one is the base choice, right? By base choice, we can influence which alpha carbon is going to be deprotonated. We can use that big bulky base and low temperatures to make our alpha carbon, our more accessible alpha carbon deprotonated, right? That bulky base gets to that more accessible alpha carbon easier. So that's our enolate ion. Or we can use our teeny tiny base and high temperatures to perform that more substituted, more thermodynamically stable enolate ion, right? So base choice, that very first step, dictates which one of these alpha carbons gets deprotonated, all right? And then in our notes now, we have these three examples of electrophiles that we can use. Alkyl halides, our very first electrophile that we were introduced to in this course, right? Great electrophiles, because that carbon left relatively electron deficient by that polar bond, and it's got that great leaving group on it, right? So it can accept a pair of electrons without breaking its octet. We got two new electrophiles from these past few weeks. The first one were ketones and aldehydes. They have that electrophilic carbonyl carbon, so we can use a ketone or aldehyde as our electrophile. We called these aldol addition reactions because our product, it's like a combination of alcohol and aldehyde, which it should be aldehyde or ketone, but they just rolled with one name. I don't make the rules here, all right? But we have both a carbonyl group and an alcohol group in our product. And then we could also use a ester as our electrophile. Esters also have electrophilic carbonyl carbons. the big difference between an ester and a ketone or aldehyde is they have this built-in leaving group. So in the course of this reaction, we kick off that methoxy group and we reform that carbonyl. So in our Claisen reactions, which again use esters, we get 2 carbonyl groups in our product. All right, so we can use either one of these electrophiles with our new enolate ion nucleophiles. Okay, so base choice was the first thing that we illustrated with these examples, and then our different electrophile choice was the next thing that we illustrated with our examples. Okay, cool. All right, so we got one more topic to cover in this one, and I'm going to be honest, it's kind of a pain in the butt, so we're going to introduce it here today, and then we'll build off of what we do today next class. Okay, these are what are called Michael's reactions. In a Michael's reaction, you have a Michael's donor, or Michael's acceptor we're going to talk about first. This is your electrophile. All right. These are going to be ketones or aldehydes. All right, but they're very special ketones or aldehydes. Where you have a carbon-carbon double bond between your alpha and beta carbon. All right, conjugated to your carbonyl group. All right, these are called alpha-beta unsaturated. Ketones or aldehydes. Or sort of like the more slang term would be an enone. Right? Remember, an enol is a double bond next to an alcohol group. This enone is a double bond next to your carbonyl group. All right. We talked about the carbonyl carbons playing the role of what in a reaction? Electrophile or nucleophile? Electrophile. All right, we talked about our alpha carbons playing the role of what? Nucleophile or electrophile? Nucleophile. All right. We now have this new alpha-beta unsaturated ketone or aldehyde, and the whole shtick here is that beta carbon is also an electrophilic site. All right, so a Michael's acceptor is one of these alpha-beta unsaturated ketones and aldehydes, and that's because it's an electrophile at that beta carbon. All right. The Michael's donor. These are going to be our nucleophiles. All right, and this is the category that we're going to kind of build on and expand next class period. For right now, we're just going to introduce one so we can take a look at these reactions and what actually happens. All right, and this is what's called a Gilman reagent. It's another one of those organometallic reagents. All right. We have some alkyl group. It is bound to another one of those metals, organometallic. In this case, it's a copper lithium combo. All right, the only thing that's weird about a Gilman reagent is there's actually two of those R groups bound to that copper, but only one is ever going to participate in the chemical reaction. So let's just note we got two alkyl groups, but only one will react. All right, so let's take a look at a specific reaction here. We're going to take our alpha beta unsaturated aldehyde here. All right, and we're going to treat it with a 2-carbon Gilman reagent. All right, so I put those 2 carbons in parentheses with that little subscript. To be clear, these are my 2 carbons in my chemical reaction here. Right, and we're going to form a new bond between our electrophile, our beta carbon, and just like before, it's that carbon that's bound to that metal that's going to be our nucleophile in this reaction. Right? So when we draw our products here, okay, in this reaction, that pi bond between our alpha and beta carbon, that will be lost, but we're going to retain that carbonyl group, and we're going to have a new carbon-carbon bond between our beta carbon and that nucleophilic carbon in our Gilman reagent. All right, so here's our new carbon-carbon bond. We're going to lose the carbon-carbon pi bond, and we're going to keep that carbonyl group. All right, cool. So based on analogy of what we just did here, I'm going to put down another example, and I want you all to give me the product of this Michaels reaction here. All right, I'm going to pick a different alpha beta unsaturated ketone. I will say there's going to have to be some sort of an acidic workup at the end here. I'm going to choose a bigger Gilman reagent here.
everybody take a second. See if you can't give me the product of this reaction. Alright, so I have my alpha beta unsaturated ketone here, and I know that this beta carbon is going to be my electrophile in this reaction, right? So that's going to be my new bond. I'm also going to lose this carbon-carbon pi bond, so I'm going to delete that. I'm going to draw my new bond. What's going to be on the other side of that new bond has to be this carbon right here, right? The one that was bound to that metal, that copper. So I draw that new bond, that means that this is the carbon on the other side. All right, so then I just got to fill in those other three carbons from my Gilman. Had a methyl group on one side and an ethyl group on the other side. All right, so I keep that carbonyl group, but I do lose that carbon-carbon double bond, and I've created this new carbon-carbon bond here. Cool? And we can count carbons to double check. My 1, 2, 3, 4, 5, 6 from my original 4, 5, 6. I should have added on 1, 2, 3, 4, 1, 2, 3, 4, and specifically it would have been carbon 3 that should have been attached, that one that I colored in red there. Okay, so these are our Michaels reactions, all right, where we take a Michaels acceptor, an alpha beta unsaturated ketone or aldehyde, and we react it with a Michaels donor. That's going to be our nucleophile in this reaction. All right, and for today, we just introduced this one Michaels donor, our Gilman reagent, another one of these organometallic reagents that will create a new carbon-carbon bond. All right, and specifically with that beta carbon of our alpha-beta unsaturated ketone or aldehyde. One more thing that I want to say about this before we finish up, because it's going to be important for how we can like piggyback a bunch of reactions that we've learned onto one another. All right, these things right here, these alpha beta unsaturated ketones or aldehydes, these are the products of those aldol condensation reactions. Remember, if we perform an aldol addition and then we introduce heat, we'll get this follow-up dehydration reaction. All right, the product that we get from those aldol condensations are these things right here, are our Michaels acceptors. All right, so you can kind of see how we're going to be able to combine stuff that we learned earlier in this chapter with what we're learning here with our Michaels reactions. Cool. All right, and we'll leave it there, and then we'll pick up with this topic next class. All right, finish off chapter 23.